let's see, here we have this, okay. All right, so we have our lecture now, which is the last one before the midterm. As I've already told you last time, this lecture, the content of this lecture is not included in the in the midterm exam that we will have this coming Monday. Ishmael told me that some of you asked about Mohr circle, and although we didn't make much of it in the first midterm, I will say don't worry about it, okay? So focus only on the computation of deformations that we've done and the double integration method that we did in the case of beams. Now, we have to wrap up a few loose ends with regards to the computation of deformations. So that's the task right now. The first one is that sometimes a structure may undergo a certain set of deformations, not because there are applied loads, not because the temperature has changed or has been added, but because a support has moved, right? So what we want to do now is to expand our capability to compute deformations, so we can do it for applied loads, for temperature effects, and now also for deformations due to support motion. So we begin by saying that the procedure, of course, because we are using virtual work, remains exactly the same, in the sense that if I want to know the deformation at a given point in a given direction, I apply a unit load at that point, and then and that gives me my unit case, right? And then we have the P case, which is the loading or temperature, and in this case it's going to be or settlement, right? Now, as opposed to the before, when we had no settlements, I applied the unit load, all we were interested in was calculating M1, N1, and V1, right? And in this case we had the curvatures and so on. Now what we have to do is we have to calculate the reactions R1 also. So when we apply the 1 kip load, the structure will have a set of reactions. Then we could say that we now apply the load. But what is the load? If it's support motion, it's simply the fact that the supports move, right? And then we look at the equation of virtual work. So the equation of virtual work will say that 1, which is our unit load, has undergone a motion in the direction that we're interested in. So 1 times delta is the work of this load, right? But in this case, because the supports moved, there is also work done by the reactions. So we have to say plus the work of the reactions. Now, I could write it, I'll write it like this: work of reactions on the settlement, right? And that must be equal to what? To the integral of M1 phi p plus the integral of M1, but all those integrals are 0 in this case, because there are no stresses in the structure in the cases we are considering, because the structures are such that the settlements of the support only produce rigid body movement. So the structure tilts or moves or something, but it doesn't get stressed. So this side is therefore 0. And what we find is the formula that 1 times our deformations, or times the deformation we want, or 1 times the angle, if it was a unit moment that we applied to get a rotation, is just simply the negative of the work, right, of the reactions. And that's it. So all I'm going to do is to say, how can we systematically calculate the work of the reactions? Not that you need really a formula to do that, because it's just force times displacement. But just to have a systematic way, if you are to list the reactions R1 in a list, right? And let me use a particular structure. Actually, let me just erase everything and show it with something concrete. This thing's not cooperating today. Okay, so if we look, for example, at this, say it had a hinge here and a roller over here, so it means that I can solve it. At this point is A, then B, then C, then D. So how many reactions are there possible at A? Well, there could be RA horizontal, there could be RA vertical, there could be, I don't know, RA moment, right? So there's 3 over here, and here I could have RD in the vertical, let's say. So those are all my reactions, right? So if I am interested in computing, let's say, the movement of point C, let's say I'm interested in calculating the movement of C in the vertical due to something that has to do with settlements. I have to do the same thing as every time. I have to put my unit load at C, but now I will calculate 3 reactions, right? This one, this one, this one, this one, actually 4. So I will have those force reactions, right? Now, in order not to write so many subscript A, H, V, whatever, let me just call this A, B, C, D, right? So A, B, C, D. Then I can say that my reactions R1 are in a vector, and I can put them in any order I want. And I can use any sign convention I want. So I can say this sign convention is positive. So A, B, C, and D, those are my reactions due to the 1 kip load. That's all I need. When the problem is a settlement problem, that's all I need from the 1 kip load, the reactions. Once I have the reactions, then I need to simply list what are the settlements. And the settlements is what the problem says they are, right? For example, the problem could say that the support at the fixed end, at capital A, the support at capital A, let me change this to A, B, C, and D, so it doesn't get confused with this A, B, C, D. So I could say that my support at A, for example, has moved downward 2 inches. Okay? Has not moved horizontally, but it has rotated by 1 degree. In other words, my footing here, which was like this at A, I find that it has moved down and that it has rotated clockwise by 1 degree. So that my footing now looks like this. It's moved down 2 inches and it has rotated clockwise by 1 degree. So let's say that that's what happened to my footing at A. Then what are my settlements at A? Well, in the horizontal direction, nothing, right? On the vertical direction, I have 2 inches, but those 2 inches are in the opposite direction of what I considered positive in the reaction. So that would be minus 2 inches, right? Now, in the angle direction, the rotation, I have a rotation of 1 degree. And it is in the same direction that I consider this moment to be positive. So that would be 1 degree, which in radians would be 1 times pi over 180, right? So that's my rotation there. And then at D, nothing happened. Therefore, my reactions due to the one-kip load are wherever they are. My settlements in correspondence and with sign conventions that are consistent are in S. If we accept that notation, then we can write that the work is simply the product of this times this. It's just this times this, plus this times this, plus this times this, and so on, right? Just like that. Now, we want to be a little bit more elegant mathematically, right? So to be mathematically correct, you can't multiply two vectors of the same size with a, because there's no such thing as R times S. So if you want to really get this one times this one plus this one times this one, what you have to do is write one of the vectors horizontally and the other one vertically and then multiply. So we could say that 1 times delta plus the work of the loads, and I'll write it like this. It's just R transpose times S, and that is equal to 0. So this is the formula that we just learned. This is the work of the loading of the reactions due to the one, let's call it R1 if you like. So this is the work of the reactions due to the one-kip load acting on the settlements. So you can see that the delta is the negative of the work due to those reactions. That's it. Okay? Can there be any complications? No. If it's theta, it's the same thing, except instead of applying the one-kip load, you apply a one-kip moment. So I think that's it. The other thing is that you just have to make sure that you don't mix up units. You know, that you don't use inches and feet and things like that at the same time, because then the thing doesn't work, right? You have to stick to a given set. So let me illustrate it now in a particular example. So I'll erase here. I will move the formula to the corner and make it a little bit smaller so we have a little more room. So 1 times delta or 1 times theta equals, plus, you could say equals the negative, but I've just plus R1 transpose times S is equal to 0. That's the formula that we are going to be exemplifying. This is in the middle somehow. Okay, we're going to be exemplifying that formula, which is just simply saying there is no work done internally, so the work of the one-kip load is plus the work of the one-kip load reactions on the settlements must be 0. Okay, so let's consider a concrete application. Let's use that same structure that I was looking at. I think in this case I gave it some specific dimensions. Let's see, did I? It doesn't really matter, I guess. I can just change it. I think I used 5 feet, but I don't find it. Yeah, I think it's here. Yeah. Okay, so let's consider this problem. So we have a structure like this, in which there is a hinge here, and a roller on this side. This distance is 5 feet. This distance is 5 feet. This distance is 10 feet. Okay? That is a hinge, meaning there is no moment there. And we have, for labeling purposes, let's say A, B, C, and D. So let's use the same thing that I asked before, but actually let's solve it now. So question. Find delta C in the vertical direction due to 2 inches downward settlement at A and 1 degree rotation clockwise at A. Okay, find delta C in the vertical direction due to a 2-inch settlement at A and a rotation of 1 degree at A also. So, as in every problem on deformations using virtual work, as soon as we know the question, find whatever. That means we apply a unit load at whatever, or a unit moment if the question was a rotation. So we take our structure here, and we say, actually I don't really care if it's settlement or not. I was asked to find the deformation at point C in the vertical direction, so I have to do this. Okay? I have to put a 1 kip load in the vertical at point C. Now, if the problem were from before, that is, if what we're going to be producing the deformation were loads, then we're going to have a P diagram with MP and so on. If it were temperature, then we'd have to have a sketch with the curvatures and axial strains and so on due to the temperatures. But if there is only settlements, or to solve the settlement problem, it gets even easier because we don't need any of that. We just need to now calculate the reactions. So to calculate the reactions in this case, there are various ways. Remember, when you see a load at a hinge, you can think about it as being either on the left or the right. You can do whatever you like. The answer is the same. It's not on both sides, and it's not on the hinge, because that doesn't make sense. It's either on the left or on the right. So let's consider it to be on the left. So if we consider it to be on the left, and we take, well, actually wait. If I could look at the free body diagram of the whole thing, right? And that would give me that this plus this must be 1, right? That's all we would know. That this plus this must be 1. We would not be able to find this reaction because there is a moment here and so on. So the way I'm going to proceed is by taking this free body diagram first. Okay, so I take that bubble, and from that bubble we look at it like this. We have the reaction here at D. This is a hinge, therefore there is no moment, but there could be a shear and there could be an axial load, and the 1 kip load is not there because I said it was on the left side. From this free body, summing moments about O, we conclude that RD times 5 is 0, therefore RD is 0, right? Now we've just determined that the reaction there is 0, so I erase this bubble to keep myself in some space, take this free body diagram out of the way, and now we can say on this whole free body, if you want, there's other ways to do it, but in this whole free body I already know that this is going to be 1, and we could find the moment here because we already know that, so I guess I could look at the whole free body, but let me do this just to give you a little more practice. So in this case I'm cutting to the left and I'm looking at that bubble. The 1 kip load must be in it, right? Oops, I shouldn't have erased here. Remember this free body, we didn't have the 1, we had something here and there was a shear and an axial, so this shear was 0, right? Given the fact that this was 0, and that is 0 also. So when we get to this free body here, and I look at this like this, I have 1, 2, 3, right? I see the 1 because it's on this side, There is a shear here, but we've already seen that that shear is 0. And there is an axial, and we've seen that that axial is 0. So this is our free body diagram here, right? Now, summing forces in the y direction, this reaction is 1 kip. Summing forces in the horizontal direction, this reaction is 0. And summing moments about A equal to 0, we find that we have 1 times 5. So this moment is 5 kip feet, right? And we finished. So I will do what? I will come here. Maybe I don't need this. I can just use this free body, this drawing with the 1 kip, to show that I have nothing here, 1 here, and 5 kip feet moment acting at that point, right? Okay, so if I want to list my reactions in a vector, I have how many? Well, of course there's a 0 here. I have 1, 2, 3, 4. You can choose any order you want. I'm going to say, I'm going to start at A, and I'm always going to go horizontal, vertical, rotation. And then I go to the other one. If there is no horizontal or rotation, I don't need to list those zeros. Doesn't make sense, right? So here I would say at A we have nothing. We have 1. And we have, now I can choose the sign convention whatever I want, right? Let's say I choose that to be positive. So 5 kip feet, that's 1 kip, 5 kip feet, and what else? And on the other side, I got 0. So those are my reactions due to the 1 kip load in the order that I decided to use. Then I list my settlements in the same order with the same sign convention. Therefore, the problem says how much horizontal movement took place at A? Nothing. How much vertical movement took place at A? 2 inches, right? So since I'm using feet here, I'm going to say 2/12 of a foot, right? That was in the vertical direction. And was that a plus? No, it's a minus, right? Because it says it's downward, and I call this one positive upwards. So this is minus, right? Now, is there a rotation at A? Yes, it's 1 degree. Now, is it plus or is it minus? Well, it says here that it is clockwise, that way. But I am using 5 counterclockwise plus, so this is also negative. And it's 1 degree, therefore it is equal to 1 times pi divided by 180, because as we all know, you cannot work in degrees, you have to work in radians, right? So minus 1 times pi over 180. And then we finish with A and we go to B, and in B nothing's going on in the vertical direction there, which is the only reaction, and so we have our settlements. And we finished. So, to find the answer that we were asked, we say 1 times delta at C plus the work, which is R1 transpose times S. Just for mathematical consistency, I'm going to write it correctly. 0, 1, 5, 0, multiply times 0 minus 1/6 minus pi over 180 and 0. Therefore 1 times delta at C plus. Now this is mathematically correct, which means 0 times 0 plus 1 times minus 1/6 plus 5 times minus pi over 180 plus 0 is equal to 0. That's what this says, right? Therefore we have 1 times delta C passing to the right side is equal to 1/6 plus 5 pi over 180, and that means that delta C is that in feet. Okay, that's it. Of course, as I said, you could have multiplied this times this times this times this. It's just that the operation r times t does not exist mathematically, right? A vector, you want to multiply times another vector, they have to be like that to get a scalar, or the other way to get a matrix. So let's do another one, or not another one, but on this same thing. Let's say that the question was not to calculate the vertical displacement at C, but let's say that the question was, oh no, I'm sorry. Do I want to use this again? Let's see. Yeah, let's do that one real quick. Let's say that the question was calculate the vertical displacement at C, just like now. But what we have is a settlement of 2 inches at D. Right? So we get a settlement of 2 inches at D. So since we were asked for the displacement at the C, we have to apply a 1 kip load, and we've already done that, and those are the reactions. Now the settlements in this case are nothing is going on at A, right? And at C, at D, assuming op is plus, we have minus 2 over 12 in feet, right? Now when we do S transpose, I'm sorry, I used R transpose. It doesn't matter which one you transpose, but let's say if we do R1 transpose times S, then it's this times this times this times this times this is 0, right? Therefore we find that delta C is equal to 0 if what we have is a vertical settlement of the support at D. Why is that so? Well, it should be more or less evident, right? Because if the support D settles down, all you have is this, right? That's what happens. And so the point at D, at C, does not move because the support at D settles. Okay? Let me see. Do we need a little more or not? Maybe. Let's just do one little bit more. With that, how can we do something a little more? So let's say we have our same structure. We have the same structure, but let's say that we are not interested on finding the deformation of point C, but let's say we are interested on finding what? Let's say we're interested on finding the angle at C on the left side. Why do I have to say on the left side? Because there is a hinge at C. And when there is a hinge, there is discontinuity of slope, and therefore the angle on one side need not be the same as the angle on the other. If I want to calculate the angle at another location on a structure where there is continuity, then I don't need to say on the left or the right, because the slope, the tangent at the point, is just 1. But at point C here we have a hinge, and therefore the tangent to the structure can be different on the left and on the right. And so this is we would normally call the left the negative side, the right the positive side, and we would say we are interested in knowing, let's say, the theta c on the negative side due to some settlements, right? I don't even have to know what the settlements are to start my problem, right? Because the question is, find theta c on the left side, so I need to already know that I have to apply a unit action, and in this case I'm going to call it kip feet because the units are kind of relevant in this problem when settlement is the issue. And I have to apply a 1 kip load and I have to solve for the reactions. So that's it, right? So I've applied my 1 kip load on the left side of the hinge, and now I want to calculate the reactions. So first we take a bubble, let's say on this side, and from the bubble on that side, this is a shear, that's an axial, this is my reaction at D, this was D, right? And from here it's evident that RD is 0, right? And that this shear is 0 and that this axial is 0. Now we take the bubble on this side, that includes the 1 kip foot moment. There is no shear, there is no axial because they are just the transplants from that side, and we have here the possibility of 3 reactions, right? So some of the forces in the y direction tell me that the vertical is 0, some of the forces in the x direction tell me that the horizontal is 0, and some of the moments tells me that this moment is 1 kip foot. So just like that we finished, and we find that our reactions are listing in order: horizontal 0, vertical 0, moment, if I take that convention to be positive, 1 kip foot, reaction on the other side 0. So those are our reactions due to the unit load, or unit moment in this case. Now we list our settlements, and in order to list our settlements I have to say what they are. So what do we want to say? Due to some settlements, let's say the settlements are I don't know, three inches upward at A, okay, 3 inches upward at A, and that's it. Let's say that that's all we have. 3 inches upward movement at A. So this point moved up 3 inches. And we want to know what is the rotation to the left side of A. Then our settlements would be nothing in X. If I take up as plus, it doesn't really matter because I hadn't made a sign convention here, I would say 3/12 in feet. No rotation and nothing happening at the other point. So if we have R1 transpose times S, which is the work, we'd see that it's 0 times 0, 3/12 times 0, 0 times 1, and 0 times 0, so we get 0, which means that 1 times the rotation at C on the left side plus 0 is equal to 0, so the rotation at C on the left side is 0, right? Now, why is the rotation on the left side of C equal to 0 when we move that point up? Because what happens in this case, physically, is that this thing moves to here, that thing moves to there, the column is now like this thing stays like this and moves to here, and this thing takes the tilt and looks like that. So that's all that happens, and as you can see on the left side, there is no slope, right? But this drawing tells us that had I asked the question about what was the rotation on the right side, I should get something, right? Because that is tilted on the right side of C, right? So let's then solve it on the right side with the same 3 inches upwards, right? nothing is useful from before, I erase everything. And clean it up a little bit. Okay, so we have our structure. It's a little wet. We have our structure. Well, couldn't get it. Maybe it's the marker. Okay, so we have the structure, we have the hinge. And we are interested on what we say, the rotation on the right side of the hinge, right? So this is A, B, C. We are interested on the rotation on the right side of the hinge. Therefore, we have to apply a unit moment on the right side of the hinge. And let's say that I do that. And so I have here a 1 kip-foot moment, which you could apply in any direction you want. I just chose counterclockwise. So this is a settlement question, therefore it's a matter of calculating the reactions due to the 1 kip load condition or the 1 kip moment condition and calculating the work that they do on the settlements. So we begin with our free body diagram on this side. And from the free body diagram on that side, I see the 1. I see my reaction here. There is, actually I'm going to take this one in the right direction so I don't need to use negatives. This is like this. Then this is going to be like that and like this, right? So some of the forces in the x direction equal to 0, that horizontal is 0. Some of the moments about O will tell me that this must be, this is R, let's say, so I have to say R, remember this was 5 feet, so R times 5 clockwise minus 1 equal to 0, so I get that R is equal to 0.2, right? So we know that this reaction is 0.2. If we now look at the sum of the forces in the y direction, this shear is 0.2. Okay? So now we take a free body diagram of the other bubble crossing the hinge and we go something like this. There is the hinge. There is no 1 because that was on the right side. What we do have, however, is that shear, which is in the vertical direction equal to 0.2. We do not have any horizontals. And we have here the possibility of 3 things, right? So, summing forces in the x direction, that is 0. Summing forces in the y direction, this is 0.2. And summing moments about this point, remember that was 5 feet. This 0.2 times 5 must be equal to this, and this is therefore 1 kip foot, right? So I'll transplant them to here. There is a 0.2 vertical, there is a 0 horizontal, and there is a 1 kip foot moment acting at that point. And we can erase, right? We can erase. And we have our reactions. So what did we say? So let's list them. So our reactions are 1R, starting here, nothing horizontal, 0.2 vertical. I'm going to call that positive, so 1 kip foot positive counterclockwise. On the other side, if I take up vertical, well actually, I don't know if you want to take it up or down, it doesn't really matter. I'm going to say, yeah, up. So this is minus 0.2 kips. But I could have put plus 0.2 kips and then that would have been my positive. So, what are my settlements? Well, in the horizontal we said nothing's going on. In the vertical we said that that point A moved up 3 inches, right? So that's 3/12 of a foot. In the rotation, we said it didn't rotate, and nothing was going on this side. So the work is R1 transpose S, and that is equal to this times this, plus this times this, plus this times this, plus that times that. So we get 0.6 over 12, 0 and 0, right? So 0.6 over 12 is our work, and therefore we find that 1, in this case 1 kip foot, right, times theta C on the positive side is equal to the negative of that, which is minus 0.6 over 12, right? Did I get that right? It looks like there is an error somewhere. Wait. 0.21 minus 0.2. Yes, all that is correct. Wait a minute. Yes, that's fine. No error. So 0.6 over 12 is what? 0.05, right? Negative, that's the work. This was, I'm sorry, the work was this much, but it goes to the right hand side, and so we get minus 0.05 radians. Okay, now why is it minus 0.05 radians? Does it make sense? Well, let's remember, this point moved up 3 inches, right? As we argued last time, that means that this point moves up 3 inches. And we saw that the left side didn't rotate, so this one is flat here. And then this one goes like this, right? So that point has moved up 3 inches. So how much, what is the tangent of that angle? Which is approximately equal to the angle. It's equal to 3 inches, which is 3/12, right? Divided by what? By 5 feet, right? Therefore, we have 3 divided by 60, or 1 divided by 20, or 0.05, right? Which is this. Now, why is this negative? Because the rotation is clockwise, right? To the right side of C is clockwise. But we applied the 1 kip moment counterclockwise. So what this number is telling us is the rotation is not counterclockwise, the rotation is clockwise, right? Clockwise, opposite to the 1. All right? So with this, I will consider the part on the computation of deformations due to settlements done. I have asked Ismail to prepare or to pick up from somewhere 1 or 2 simple problems that you can do to practice this. And as you can see, all that this entails is just the same as before, right? You need to know statics. If you know it, if you know how to do it, and you don't make an error in statics, then you're fine. If you do not, if you're having problems with statics, then that's it, right? Can't get the reactions, can't do this, can't do that. All right, so let me stop here to keep the size of the files reasonable.